Okay, so we have 20, AMC 12B, number 17. So how many polynomials of this form, where A, B, C, D are real numbers, have the property that whenever we have R is a root, then so is -1 plus I root 3 over 2 times R is also. So like the question is kind of obvious, but basically it's telling us we want to find the number of polynomials, right? That satisfy the condition where the constant term is 2020. And whenever we have a root r, then when you multiply r by this complex number, you get also a root. And how many polynomials do we have in this condition, right? So the first thing I'll say, like, kind of explore a bit, but before we kind of do, since we have the relation between the coefficient and the root, that's a good time to think about the Vieta. But I don't really know A, B, C, D. I know only the constant term. So when you think about the Vieta, like, the sum of the roots or product of the roots or pairwise product and stuff like that. So we just need to solve it like negative of like second highest term coefficient divided by highest term. Like if I want to say the roots are x1 through x5. So the sum of the roots, I'm going to call S1, which is x1 plus x2 plus whatever. So it's going to be negative of a divided by this. But if I want to do x2, which is basically, we call symmetric sum sometimes, this coefficient divided by 1, which will be, this will start with negative, but now we do a positive, so which is b. And then if I want to do s3, which is you multiply 3 roots all together, all different ways to get the product of the 3 roots, and we called s3, and that should be c over a, but we start with negative. This was positive, so you should say minus c, and then s4 is going to be just d, and then s5 is going to be negative 2020. So I'm just reminding the Vieta for higher degrees, basically, especially for fifth degree. So we usually start with negative b over a, which is like negative b is representing the coefficient of the highest second degree term, and then a representing the coefficient of the highest degree term. But in this case, like our second highest is a, and the highest degree coefficient is 1. So we just start with negative a over 1, and then we got this one. So this is just the review of the Vieta, basically. So now we can just say, okay, we have roots. I'm going to say those are x1, x2, x3, x4, x5, right? So these are going to be minus 2020. So again, in this case, in this problem, it doesn't really matter. So you will see why soon. But it's just good to know the Vieta for the higher degrees anyway. So my first piece of information is given this. Like, let's say we have one root is r. But another thing we should remember, since the coefficients a, b, c, d are real, so this is really important. And when you have a real coefficient, the complex solution comes in pairs, which we call complex conjugate. And then we had the fifth degree, which means we have 5 roots. But if you have a complex solution, that must be in pair, which means we should have maybe 4 complex solution, 1 real, or 2 complex, or 3 real and stuff. But at least we know we do have 1 real, certainly. I don't know what that number will be, maybe R, maybe not, but I don't really know for yet. So which is I'm going to call x1 is R, so the x2 should be the R times this complex number. So let's try this. So negative 1 plus I root 3 over 2 times R. So if this is real, then this is complex. And then if this is complex, we should know the complex conjugate is also solution. But since we do not know about this number, maybe this is complex. When you multiply this complex by this complex, maybe x2 become real, which we do not know. So which is I'm going to continue with my only property. So think about now the same property. So this is a solution. And if you are given there is a solution, then the solution times this number will be a solution as well. So which means if I multiply this number, this solution, by this complex number, I should get another solution of my polynomial. So let's go ahead and write it. So negative 1 plus I root 3 over 2 times R. This is my root for 2. And then I multiply this by negative 1 plus I root 3 over 2. And I'll simplify a bit. So negative 1 times negative 1 is just 1. And then negative 1 times positive I root 3 will be negative I root 3. And then if I multiply this by this, you get also another negative I root 3. And then multiply I root 3 by I root 3. That's 3I squared. I squared is negative 1, so that should be negative 3. So we got this over 4. But we do have R as well, times R. Okay, so when you say 1 and negative 3, that's negative 2. And then you got negative 2I root 3. If you take the 2 as a common factor and cancel with that 4, so you'll get negative 1 minus I root 3 over 2 times R. Okay, but the thing is, we got 1, 2, 3 solutions so far, right? So let's continue in the same pattern. So we got 4 root. And then if this is a solution, then we multiply this solution by this complex number to get another solution. So you will get negative 1 minus I root 3 over 2 times negative 1 plus, we multiply this by a given complex number, which is I root 3 over 2. So like, luckily this number and this number are conjugate, so we can easily use difference of square. So that will be negative 1 squared will be 1. And then when you take the negative and negative, that's positive. So you got 3I squared, which is negative 3I squared, which will be positive 3. And if you don't see this immediately, I will say just go ahead and expand as I did in the third root, and then times R. So that becomes just 1 times R, which is R, which is the same as the first root. So meaning that we do have now only, I guess, 3 solution, that is this thing. So, but we do have 5 solutions, so which means we may have, some of these roots kind of repeated, or we may have another root that is not actually R. So we could say, let's say there's another root, let's say W. Then if you have W, then W times this number will be another solution, and then W times this number will be another solution, but that will make another 3 solution that is different, so which is 6 solution, but it's not possible since we have 50 degree, meaning that we don't really have any other solution other than these 3, so which means we should have these 3 roots are repeated somehow. So another thing we do have, when you multiply the roots, so you got negative 20, right? So which is when you multiply these roots some number of times, you should be getting this guy. So what does that tell us? Let's go ahead and write that a bit. So the R, I don't know how many R's do we have, but maybe 1 or 2, maybe 5, but 5 is not anyway. It's not the case anyway. And then negative 1 plus I root 3 over 2 times R, and then times negative 1 minus I root 3 over 2 times R. So again, this guy is a solution. So I don't know how many times this is going to repeat. So I'm going to call that B. And then this is going to repeat, let's say, some number of times. That's C. So the sum of those A, B, C's, A plus B plus C, should be 5 because of degree is 5. And the question is that we should look for. So when you multiply the roots this many times, you got minus 20, but that's a real number. So based on our exploration, R is the real number and the other 2 is complex. So which is why in order for us to get the real, so this number and this number should be a complex conjugate, or like when actually they are complex conjugate anyway. So when you multiply this by this, you actually end up getting a 1. So we just saw right here negative 1 minus I root 3, negative 1 plus I root 3. When you multiply this number by this, you get just real number. So which means in order for us to multiply these two, the bases, the power should be same, right? So the B and C has to be same. So we can say this is 1 and 1, so that will make this is 3, or this is 2 and 2, so that will make this is 1. And there's no other ways to get them. So if I want to try, let's say, this second degree and this is first degree, right? Then you can try multiplying, but it doesn't work because we know that R has to be the real number based on our reasoning. So if R is real number, this is complex, and then that's also complex, then conjugate will be available as well. But these two numbers are already conjugate, so which is why we cannot really have something else. So this number's conjugate will be this number, this will be this one. So which is why we cannot have different exponent. So we just have 1 and 1 and 2, 2 for the B and C, and then that will give us only 2 polynomial. So I hope that was clear. So if this wasn't kind of obvious to you at first, and I will say it's good to review the complex roots and do some more problems on it. So I think that was interesting question. I'll see you in the next video.